All right, recording. My name is Marco Peterson, and this is the end of the semester report for optical satellite component tracking and classification via synthetic CNN image processing for on-orbit servicing and assembly. It's a long title, but what does that mean? So this is a nice little diagram of how we've done it in the past. Uh, there is several missions sent out to both the ISS and the Hubble telescope. This picture over here is the Hubble telescope. I believe a total of 5 repair and refit missions with the Hubble telescope, and we did it with humans back then. This picture over here on the right is how we would like to do in the future. Use robotics to either put trusses together, or let me see if I can pull this up. There we go. This is more of an assembly task, putting trusses together for new orbital platforms, space stations, so on and so forth. And this one on the bottom is more of a servicing task, satellite to satellite, either refit, repair, or refuel operation. So how do we get there? So need to gather up synthetic data creation. We'll see why here in the next slide. Train a convolutional neural network and perform object classification and localization. Fundamental problems to solve. How do we acquire that training data? How do we train that data? And how do we use that information for real-world manipulation? Neural networks require a large amount of training data. So if that training data is unavailable, you will use, obviously, the next best option is synthetic data. Reasons you want to use synthetic data: if, for example, you're prototyping or you're performing some kind of 3D printing operation, there's a lot of research to actually 3D print those trusses up in orbit. And you're trying to do some kind of camera-based navigation or localization or identification, you're going to need to use a synthetic environment to train that neural network. The second reason, obviously, is you're in an austere environment. Either it's unpractical or too expensive to go out and collect that real-world data. Synthetic data is your next best option. The problem we're trying to solve has both of those problems integrated in it. We're using 3D printed trusses or some derivative of 3D printing where it's assembled in space, but it's not yet in space for us to go up and take pictures of. And obviously the second problem is space is still prohibitively expensive, so you're not going to send up a camera to go out and take these pictures. Or for any other space environment, it just doesn't have to be there now. It's a space station, which is relatively close if you're trying to do navigation on Mars or any other celestial body for that matter. Our baseline. So this is where we're currently at. The Unreal Engine synthetic environment is on the left, and it's running a neural network to do computer vision tasks for detection and classification and localization within that picture frame. And then the picture on the right is our real-world validation. So it's detecting solar panels over here. So it's 97, 98% confident that those are solar panels. Solar panels are kind of the easier ones to pick out. And then on the left here, obviously this is the environment it was trained in, so it does relatively well, especially with these trusses are joined together, and it's able to detect that this is 2 trusses instead of 1. It does a little bit worse on the solar panels down here during the occlusion. So how do we get there? Now back out of this, go to the Unreal Engine. So this is the environment that I created inside Unreal Engine 4. It just has a simple International Space Station on it right now. I can import any assets that exist as an OBX file or a 3D printed STL file. Basically, if it's a 3D printable part, I can import it in the Unreal Engine, and I can perform, I can pull out synthetic imagery on it, and basically any background. But for this use case, it's the International Space Station. What's kind of nice about this is the Unreal Engine has dynamic lighting, so if I go to the dark side of the station, obviously everything goes dark, as it should. And this is one of the variances that you're going to have to solve on orbit. Lighting is a big variance you're going to have to deal with, and then rotation obviously is another variance you're going to have to deal with, but rotation's a little bit easier one to solve than this extreme dynamic lighting situation. So that's the synthetic environment that we're currently working with. We'll go over here to the flowchart that we have. This is results. We'll get to results later. So everything started out as a SolidWorks file, and then it was pushed to an STL file. From that STL file, went 2 different ways. Those trusses were sent to a 3D printer and then printed into the real world, and then we did some 360 imagery on those trusses to pull out like real world data on the trusses, and then those trusses were also sent to Blender. Blender converted them to an OBX file, which then can be accepted by the Unreal Engine, and that's how you see those trusses existing in the Unreal environment. And then we scrubbed a bunch of real world images over from Google and pushed. So the images over here on so this was the training data, and then these two columns over here were the validation data. So the 3D printed part and all the images from Google were in the validation set, and then all the images, synthetic imagery that was pulled from the Unreal Engine was the actual training data set. So after we pulled the images, we labeled them using this open source tool here called Label Image. You can find it on GitHub. You essentially just upload all your images and go through and do the laborious task of labeling everything that you're trying to identify. So we did that for about 600 photos, and then we did some arbitrary rotations to about 20% of the photos to get the rotation variance down. And then we pushed it through a neural network. The neural network we chose, the neural network we chose was YOLO4. Mainly because YOLO4 is able to be trained on off-the-shelf commercial GPUs, either 2080s or 3080s. And it also has a light variant, YOLO Lite, which can perform computer vision tasks on hardware that does not contain a GPU. For example, your Raspberry Pis or your NVIDIA Jetsons. And yet, the lower hardware GPU is especially, or lower spec computing power is especially important for space applications, because most of that hardware is lower spec than what you would find on Earth, because the PCBs have to be bigger, because there's a lot of potential for bit flipping to happen due to ionizing radiation and so on and so forth. So to be able to identify a truss where it's at in space using a lower spec camera up in orbit is important to the problem set. But the results that we currently have, using a mean average precision of 50, you can see over here on the left is the accuracy within the synthetic environment, and then over here on the right is the accuracy within the real world environment. So within the synthetic environment, the CNN is able to pick up, like, hey, the Canadarm at 92%, but only can do 10% in the real world environment. That's partially because the Canadarm in most of the pictures that we scrubbed was disconnected, or well, it was connected, but it was the ISS was not in the background. And the same thing for this Zavada spaceship. There is also an error on my part of the Zavada spaceship. It picked up the Soyuz space capsule as a Zavada spaceship 9 times out of 10, and it would obviously get back a false positive. So to remedy this in the future, what I'm going to do is either generalize it and just name everything as a spaceship, or go back through and relabel everything as like, hey, this is Soyuz and this is Zavada, to differentiate the two. And then to further bump up these numbers, I think down here in the future work, I'm going to implement a tool called domain randomization, which is just randomizing the data set to include a lot more variance, so I get less false positives throughout the training epochs. This graph down here, so I did over 8,000 iterations. This red line is the mean average precision as we go over more and more iterations, and this blue line is the loss function going down. So those are the results. I'm going to tack on a 2-minute video of just, it's the demo video going through this synthetic environment and then pushing over to the real world environment. Got some videos of astronauts climbing around the space station in their helmet cams, and I'm trying to do object detection on things that we already have in the synthetic environment and the real environment from those helmet cams on the astronaut headsets.